All right, here's how we're going to do it. We're going to actually use note 79, the rational zero theorem, that says the f of x is a polynomial with whole integer coefficients. That indicates that all the rational zeros are somewhere in the list p over q, where p, the numerator, is a factor of the constant, which in this case is 6. That's the constant, the number at the end of the polynomial, while the denominator has to be a factor of the lead coefficient. In this example, the lead coefficient, which is a number multiplying the highest power of x, is 2. So let's make our list. Step 1. Let's make our list of potential rational zeros. Okay, so we've got p over q equals, put a plus or minus out in front so we don't have to worry about putting plus or minus inside. And on the numerator, we're going to list all the factors of 6. First, there's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. In the numerator, we're going to list all the factors of the lead coefficient 2. That's plus or minus 1, plus or minus 2. Now, we're going to refine that list, plus or minus, by taking the numerator 1 and running it over each of the denominators. So we have 1 over 1, which is 1. 1 over 2, which is, I'm sorry, let's go all of the numerators over 1. 2 over 1, 3 over 1, 6 over 1. Okay, now let's do them all over 2, but don't repeat yourself. Let's go 1 over 2, that's 1/2. And then 2 over 2, that's 1. We already have that, so don't write that one down. Then we have 3 over 2. Yes, write that, 3/2. Then we have 6 over 2, but 6 over 2 is the same as 3, and we already have that, so don't list that. There you go. That is a list of all of the potential rational zeros for this polynomial. And don't forget, there's a plus or minus in the front, so there's really twice as many potential rational zeros. And you see there, some of them are positive and the other half are negative. Okay, now, what do we do with this list? Let's go to step 2. We're trying to find the rational zeros. Which ones are rational zeros? We're going to test them. Test for the zeros. How would we know if one of these numbers is a zero or a root of the polynomial? Well, we'll synthetically divide, and then if we get a zero denominator, we'll know that we have a root. That's the, what did we call that? The remainder theorem. If the remainder is 0, we know we have a root. Okay, so first we're going to synthetically divide by positive 1. We're going to test positive 1. Okay, here's positive 1, and we're going to divide it into the polynomial that has the coefficients 2 space, 1 space, negative 13 space, and 6. Make some space, bring down the first coefficient 2, multiply, add, you get 3, multiply, add, you get negative 10, multiply, add, you get negative 4. Oh no, that's no good. It's not equal to 0. So that means that 1 is not going to be one of our dudes, one of our roots. Let's test number 2, the number 2 in the list. Let's synthetically divide and hope that we get a 0 remainder. Coefficients of our polynomial, 2, 1, negative 13, and positive 6. Make a space, bring down the first number, 2. Multiply, that's 4. Add, you get 5. Multiply, 10. Add, you get negative 3. Multiply, negative, oh my goodness, look at this. Oh, happy day. Happy face, right? Happy face, because we got a 0 remainder. And what does that mean? That implies that, shall I call it x or shall I call it a? I'll just call it x. X equal to, that was the number we synthetically divided by, is indeed a 0. And it's rational, right? Rational numbers are whole numbers, basically. Positive or negative whole numbers are zeros of the poly. Excellent. We proved that by synthetically dividing and getting a 0 remainder. Okay, now, since we found one that works, you can slow down here and use the result to do this next step. Step 3, you can start factoring. Once you've found a root, because you synthetically divided by that number and you got a 0 remainder, you can use it to start breaking down your polynomial, because if we get this thing completely factored, we know all of the zeros. So p of x, which was originally 2x cubed plus x squared minus 13x plus 6 is now equal to x minus the 0 we just found, 2, times, use the bottom row down here, the bottom row, as coefficients of a polynomial 1 degree lower than the cube that we originally started with. So there's a 2 times x squared, and then a positive 5 times x, and then a minus 3. Now, at this point, we still have to break down the second degree factor. We can just start the same process of synthetic division again, or we can just use methods that we already know for factoring second degree function. We can use a quadratic formula or factor by guessing. I'm just going to go ahead and guess. I'm going to get, let's see, 2x in the first position and x in this other first position, and then a minus 1 here for the second position and a plus 3 in the, okay, there we go. All right, now, if you set each of these factors equal to 0, you'll get the roots or the zeros of this polynomial. Okay, so x minus 2 equals 0 yields x equals 2. 2x minus 1 equals 0, solve that, you get x equals 1/2. X plus 3 equals 0, solve that, and you get negative 3. So we have found all of the zeros. Now, they didn't ask us to do that, but okay, we went further than we needed to do. We found all the zeros, but they asked us to find the rational zeros. We found all of them. And by the way, this is important to note. These things would appear on the graph of this polynomial if you had to graph it, which you were not asked to do. These values would be actual x-intercepts. Like here's negative 3, here's an x-intercept, and then 1/2, say, would be over here, and then 2 would be like over here. And if I actually took a graphing calculator, I can see what's happening here. We actually have a high point at 6, and the graph comes down from there. It goes to the negative 3. It comes back up over here. It goes through the 1/2. It dips down and comes back up and goes off to infinity. So we were not asked to graph it, but I just want you to realize that we found the roots, negative 3, 1/2, and 2, for the graph of this polynomial.